So the ESP32 C3 is potentially an awesome microcontroller, but these dev boards that you can buy on AliExpress super cheap have one major flaw. It's that the Wi-Fi on several of them is not very good. So in a lot of my past videos, I've wanted to use one of these. So for example, my last video where I wanted to hide a server inside a light bulb, one of these would have been absolutely perfect, but it's absolutely no use if the Wi-Fi is not strong enough that you have to be basically stood directly next to it to get it to work. So that's a bit of a problem because they're so cheap and so good. I bought a massive pile of them and yet they're useless to me. They don't work. So what can we do about that? And that's the focus of today's video. And let me start by saying, so if you just go and buy some of these on AliExpress, these look similar. So obviously these two look identical and this looks slightly different. It's really weird. If you search for the same name, you'll see all different types. They all look potentially the same or slightly different. And you don't know which ones are good and which ones are bad. So the first criticism of these particular ESP32 C3 mini boards is that this ceramic antenna is not well spaced. It's too close to some of the components, for example, the microcontroller, the crystal oscillator. And if you look at the manufacturer's recommendation for this actual chip antenna, you'll see it recommends some free space around it. So if we take a look at this board here, you can see here's the antenna. If you just look at the silk screen and the wires on the board, you can see there's nothing around the antenna. And I can tell you now that the Wi-Fi on this particular C3 is much, much better than these two. So I'll put a link to this one. That's pretty good, but what can we do when we have a bag full of these like I do? So if you look at them, you'd think they're the same. They look identical, but actually if we flip them over, immediately see that they're not exactly the same. For a start, the silk screen's different, so the labels are in the different places, but also you can see the wires and the tracks are all different. So they're actually, even though they look identical from this side, they're basically different boards and they're going to have different electrical parameters and they're going to behave differently. So it's very hard when you're looking for cheap microprocessors on AliExpress to see the picture of them and think, oh, that one's going to work and that one's not. So we need a backup plan, a plan for what we're going to do when we get a big bag of these and they're essentially useless. And the way I tackled this is basically I did some research online and quite a few interesting articles about what we might do to improve the performance of the Wi-Fi on these boards. Let me show you an awesome webpage I found by Peter Neufeld, where he's basically designed a quarter wave antenna and soldered it directly to the chip antenna on the ESP32. It's pretty simple. It's just a single piece of wire that has a loop of around 5 millimeters diameter either side of this ceramic chip antenna, and then it's got a straight length of wire here measuring around 31 millimeters. 31 millimeters is no coincidence. That happens to be a quarter wavelength at 2.4 gigahertz, which is the Wi-Fi frequency we're interested in for this C3. So in this video, I'm going to actually build this, but I'm going to look at how it performs when we're transmitting and receiving, and I'm going to look at optimizing the length of that antenna to get the maximum performance out of the actual system. And finally, although this is awesome and you'll see some pretty amazing improvements, it's a bit big. Okay, so let me just show you. So here is an example I've made. Obviously it looks like the one on the website, but the issue with it is it's the antenna's longer than the actual board. So you lose some of the advantage of having such a tiny microcontroller board by implementing this fix. I mean, this doesn't make it massive and it makes these boards usable again. So it's really cool, but I wonder if there's anything we can do to maybe make it a little bit smaller, probably at the expense of some performance though. But anyway, let's crack on. Just before I begin modifying that ESP32, what I actually wanted to do in this video is shown on the screen now. So I really wanted to use a nano VNA to measure the standing wave ratio, the SWR of the antenna, and tune it specifically for that Wi-Fi band. But I've basically cheaped out on my nano VNA and I've only got the version that goes up to 2 gigahertz, which is no good for Wi-Fi, right? So Wi-Fi is around 2.4 gigahertz. But just to show you a little bit about that before I move on and do it the other way using the Arduino code. So here I've got a random antenna. I don't know what it's from actually. I just found it in a drawer. I think it might be a GPS antenna, although the frequency maybe not. And here on the screen, if you can just ignore the glare for a moment, because it's such a sunny day, which is unusual, you can actually see that the yellow line is the standing wave ratio, and at a particular frequency, so around 900 megahertz, the standing wave ratio is almost 1. And basically, a standing wave ratio of 1 means that all the power from your transmitter is going into your antenna. Might not entirely be radiated, but it's as optimum as it possibly could be. If you had a standing ratio of, say, 5, that would be an absolute dreadful antenna. That means most of the power your transmitter's sending is getting bounced back and coming back into your transmitter, which is never a good thing. So unfortunately, I can't use this, but this would be the way to do it if I had a nano VNA that worked at that frequency. But also that glare is a massive problem, so it wouldn't be a very good video. Let's crack on and do it the old-fashioned way. So in terms of coding, this actually requires none. So we're only going to use the Arduino example libraries. We don't need anything special for this. So if I just go into Arduino, I search for examples, scroll down to Wi-Fi. You've got Wi-Fi scan, which basically scans the local area for all the access points, lists them on the serial terminal, and shows you the RSSI, which is basically the relative signal strength intensity. And I'm going to be using this Wi-Fi access point, which actually creates an access point on the ESP. So I'm going to be looking at both receive and transmit. I'm definitely not an expert in radio frequency communications or anything like that, but I was reading online, and it's relatively easy to improve the receive performance of a radio. But of course, Wi-Fi is bidirectional. You need to transmit and receive, and transmitting is a lot more difficult, and you need a much better designed antenna to be able to successfully transmit. So I'm going to look at both receiving and transmitting using these two example codes. So you need really minimal equipment to do this fix. Basically some solder or soldering iron, some cutters, and a little piece of wire, and of course some safety glasses if you're soldering. I have to admit, I've been teaching undergraduates recently, and the number of students I see heading towards the soldering iron and soldering without glasses on, it's absolutely crazy. I don't like to preach, but it's so easy to flick solder into your eye, unbelievably, especially when you're pulling wires apart and trying to unsolder stuff. So I really would encourage anyone to wear safety glasses. But anyway, let's have a look at what we're trying to do. Basically, I'm going to follow what was stated on that blog, and I'm going to take my piece of wire. I've just stripped the casing off it, and I'm going to solder it to basically across the antenna in a loop, and then I'm going to come up sort of perpendicular to the antenna, about 35 millimeters for now. So I have a ruler. I'm set it to around 36 millimeters, because what I want to do is basically I want to optimize the length of this, and I'm going to do that by cutting it down. So I want to start too long and gradually shorten things. So I've made a little kink in the wire where I want my loop to start, and the loop, according to that blog, should be around 5 millimeters. So the diameter of that screwdriver is a little bit less than 5 millimeters, but when I cut it, it's going to expand, no doubt. So what I'm going to do is I'm just going to take this and I'm going to bend it around there, and then I'm going to snip it off. And then of course this needs to be at 90 degrees. So it's not perfect, but there you go. That's like fabricated the antenna there. Obviously I'm going to need to open that a little bit, and I'm going to solder it like this. So the curved bits is by the crystal oscillator. So it's going to go down, you can see, a bit like that. It's a little bit fiddly, this part, but let's give it a try. So my first test is actually going to be to see how much of an improvement in being able to receive signals we can get by adding an antenna. I'm going to do this in a few different ways. So firstly, I've got myself an official expressive ESP32 C3 development board. So this is the real one. I bought it from like RS in the UK. Cost like £16, so it's legit. I'm going to set this up as an access point, and I'm going to put it over there on the seat of my bike as a repeatable sort of access point. I know exactly where it is, and it's going to be well controlled. I'm also going to look at the signal strength to my home router, which is basically even closer. It's like 1 meter to the left of me on the windowsill. And I've also in my house got a Wi-Fi repeater. It's not a big house, but still my signal's pretty weak downstairs. So I have a repeater down there, and I'd say that's about 6 meters away through maybe 3 or 4 different walls, a door, etc., etc. So those are the 3 access points I'm going to be looking at. Put the server code on this. Then I have my ESP32, which I'm going to set up as a client, but I need a benchmark. So to do that benchmark, I'm going to use this ESP dev board. So first things first, I'm going to put the access point code onto the S3 microcontroller, and I'm going to label it S3. I'm going to upload that. Okay, that's done. So I'm now going to disconnect it, and all I'm going to do is plug my USB battery pack into the microcontroller so it creates that access point, and I'm going to pop it over here. Try and make sure it's always in the same position, and I know it's about 1.2, 1.5 meters away. The next thing I'll do is I'm going to get my dev kit 1, the sort of original standard ESP32, and I'm going to put the client code onto that. Okay, let's have a look at a serial terminal, and you can see all the Wi-Fi networks near my house. So obviously I'm going to blank them out because I don't want to sort of give away my location, but let me just unplug it for a moment, and we'll just scroll up to the networks of interest. Although they're blurred out, the top one, number 1, is basically my home network, and that is the closest to the client. So that's got an RSSI of -37. It's on channel 11. My ESP32 access point has got -45 dBm. That's the one just over my shoulder there. And here's my extension number 3 at -67. So we'll talk a bit more about those numbers in a moment. But let me just give you an example now of what the original C3 with the unmodified antenna gives you. So they have put the code on now. Let's look at serial terminal. So I think you can see immediately, well, you've seen less networks for a start, which is never a good sign. My home network is on -49. My access point S3 is on -60, and I have to scroll all the way down to network 6 to find my home at -90 dB. So that's an extremely weak signal. If you just wanted a demonstration of why the C3 Wi-Fi is not very good, there's the demonstration. It's terrible. I've got a lot more rigorous data I'm going to show you in a moment, but you get the idea. So just a really brief reminder what we're doing. So we've got a client, and that could be the original room dev kit, the original C3 Super Mini with the crappy antenna, or the new antenna on the C3 Super Mini. I've got 3 different access points. I've got my S3, which is just over my shoulder. I've got my home router, which is about 1 meter just next to me on the desk. And I've got my Wi-Fi extender downstairs, about 6 or 7 meters away. And I found this sort of useful chart online that tells you what various signal strengths mean. So anything around -30 to -50 is really great signal. Anything sort of 60 to 70 is okay, sort of usable. Anything between 70 and 80 is pretty poor. It's going to be a really weak connection. And anything down by -90 is going to be pretty crap or unusable, basically. So that's the basic setup. And here, the ESP C3 is acting, or the client is receiving. So let's have a look at the results. So here, we're looking at the room. So the original dev kits, this one here, the sort of old style ESP32. And you can see that on average over 30 scans, sort of my home and my ESP-S3 behind me are roughly similar, around -40 decibels or dBm. And then right down at -65 is the access point downstairs. Basically a benchmark case. This is a ESP everybody uses. I've used it loads myself. It works well. If we can get our C3 up to these kind of numbers, then it's going to be a much more usable device. Also, on average, this found 12.5 networks, so flicking between like 10 and 14, I would say. So looking at the original C3 Mini now, the one with just the standard chip antenna, and you can see quite a significant shift in numbers. So here now, my 2 closer networks have dropped down to around -50, -48 decibels. And the access point downstairs it's almost off the charts. It's right bouncing around sort of -76, 77 decibels. So not a strong signal. You're in this really, really unreliable and unusable regime. And this is basically summarizes what I've found in previous videos. They're just not usable. Now, this is the interesting one. I've put the new antenna on and look what happens. So immediately my home and my ESP have jumped up to around minus 30, 33, something like that, decibels. And my access point is now being seen at around minus, 58, something like this. So now everything's been bumped up into this usable sort of green or yellow area. That little antenna, so just a piece of wire, has turned this module, at least in terms of receiving, into something that actually works and is comparable in performance to the sort of conventional ESPs we're used to. So that's a massive win in my opinion. So what I've actually done here is I've just taken the weakest one, the extension downstairs, and I've calculated the average signal intensity over the 30 scans. And you can see there's actually a massive 18 decibels difference between the improved antenna and the original sort of red chip antenna on the ESP. So that's a massive win, to be honest. So from what I've been reading online, almost any antenna is going to be better than no antenna. So just sticking on a wire of almost any length onto your ESP is going to improve its receive performance. But the transmit case is much more difficult. So for a proper transmitter, you need a very good matching between your antenna and your radio. And that requires a well-designed antenna. So what I'll do is I've actually made the antenna too long on the ESP at the moment. I know it's quite a bit bigger than the quarter wavelength, which should theoretically be the optimum. So I'm starting too long, and I'm going to set the ESP as the access point now. So I'm going to put that over my shoulder, and I'm going to have the client as the S3, and I'm just going to look at the signal strength reported by the client as I change the length of the antenna on the ESP32. So this is kind of like tuning it. It's not as good as looking at standing wave ratio, but it's a great way to tune it. And I'm going to find what the optimum is. Just the text on the screen kind of explains, if you want to double your range, you really need to increase your transmit power by around 6 decibels. So if I can get a 6 dB gain, then I've almost doubled the performance of the Wi-Fi on the actual microcontroller. So that would be a massive win. So let's quickly upload those pieces of code, because obviously I need to swap them around now, and let's see what happens. I'll start with turning this one into the access point. So I've now got my C3 with the antenna as an access point. And I need to configure my S3 now as the client. So there you go. So you can see it's actually found 20 networks, which is pretty cool. So each one of these points on this plot basically represents around 30 scans, the RSSI calculated from average from 30 scans. And you can see when the antenna length was around 38 millimeters, the average was around minus 27 dBm, which is pretty impressive. That's a very strong signal. But actually the optimum's found around 34 millimeters, which is slightly longer than the calculated value, what it should be. So the quarter wavelength is 31.25, 2.4 gigahertz. But I think the key point is, I'm not showing the data here, but is when I actually set the original C3 Mini up as the access point, I was measuring a signal intensity of minus 60 dBm. So minus 60 is usable, but look how close the access point is. There's absolutely no way if you took that downstairs or something it would work. And that's why it doesn't work on, say, WLED or in any of my other projects where I need the ESP C3 to actually transmit something. But you can see if we set the antenna length to around 34 millimeters, almost improved by around 40 dBm. That's a staggering amount. That's like, I don't know, maybe 3, 4, 5 times more range. Absolutely crazy. As you make the antenna shorter and shorter, obviously the improvement drops off. I guess actually if you remove the antenna, you're back to the ceramic chip and you would be around minus 60. So that's where that's going if you ask me. So yeah, that really just shows you how easy it is to make those really cheap C3 modules usable again. But my one complaint is that the size of these things now with the antennas, so this is the chopped down version. I've basically been chopping down the length of it. The size of these is pretty big. They're not so usable anymore. What I'm going to try and do, and I know it's going to degrade performance. So you don't need to say in the comments, how could I think it was going to work? I don't think it's going to work, but I'm going to actually curl the antenna around, turn it into like a helix, and see if we still get improved performance. Won't be as good as this, but in much less space, because that would be really powerful. So let's get on with that. Let's have a look. So here's my antenna, and what I've not shown you is that I've actually had to extend by about 1 centimeter, because of course I chopped off 1 centimeter as I was reducing the length in 2mm bits. I was just cutting off little bits at a time, got down to 26mm, and then I want to go back up, and I was a little bit lazy. Instead of making a new antenna, I just soldered on a new piece of wire. When I start twisting it around, I'm not sure that's going to work, but anyway, let's see. So yeah, that was kind of inevitable, weren't it? Anyway, rather than sticking on a new piece, let's see what happens when we do this, because it probably won't work anyway. So there's loads of nice calculators online that tell you how to design a proper helical antenna. And this is not the way to design a helical antenna, I can tell you that. Even though I don't know how to actually design one, I know there's a lot more to it than simply just curling the actual antenna into a spiral. So I'm sure there's some ham radio enthusiasts or something who may be watching this video who knows this is a terrible idea. And I'm really interested in any comments in the chat to maybe how we might improve it without making it much longer. Looks a bit messy though. So I've spiraled that around now. Let's give this a go and go plug it back in. So here is the access point, minus 44 decibels. So thinking about it, yeah, that's a big degradation in performance. So we've lost around, 20 dBm, but, it's still a massive improvement over the minus 60 that the original ceramic antenna gives you. So yes, it's not as good. It's definitely not optimum. And I'm sure somebody in the comments is going to say what I could do to make that better, but it does save a hell of a lot more space. So to me, the whole point of these modules is what makes them so impressive and so useful is that they're really small. So by including this tiny little antenna, we can significantly make the Wi-Fi better and make it usable. Then it's a massive win. I mean, I'd love to quadruple or whatever the range, but if that involves using an antenna which is like, 2 or 3 times longer than the actual module itself, you kind of lose some of those advantages of having a small module. So making a little spiral antenna like this, which improves performance dramatically, maybe not astonishingly, but dramatically, but with much lower footprint, it could be a really good way forward. And it makes these unusable modules basically usable again for very little effort and little cost. So I hope you found that video useful. If you did, like and subscribe. And of course, go and pick yourself up some ESP32 C3s, because now you don't need to worry about buying duds. They're all pretty poor. You just need to solder on a little piece of wire like this to make it work again. So thanks for watching, and I'll see you in the next video.